In this lesson, we will evaluate a stride prefetcher with a stride table of 64 entries. We will consider 10 hot streams, show why prefetch degree greater than 2 can cause cache pollution, and quantify the performance impact when prefetch accuracy is less than 50%. We will do this mathematically, statistically, and graphically. First, the stride prefetcher keeps a stride table. Ours has 64 entries. Each entry learns the last address and the stride for one stream. With 10 hot streams, at least 10 entries will be active. Let's draw a 64-entry grid and highlight the 10 hot streams. Notice that capacity in the stride table is not a bottleneck here. We still have more than 50 free entries. Prefetch degree means how many lines ahead we fetch per stream. Degree 2 means we stay 2 lines ahead, which is usually safe. When degree is greater than 2, we start bringing extra lines that may be touched far in the future, increasing the chance that prefetched lines displace useful demand lines. Let's draw 10 stream lanes and visualize degree 3. We'll color the first 2 look-ahead lines green and any additional look-ahead lines red to indicate higher pollution risk. To reason about pollution, we compare how many prefetched lines want to stay resident versus a working window of cache lines. Let S be 10 streams. Let D be degree. A simple footprint estimate is S times D lines. We compare it to a local cache window W. To make the risk visible on screen, let's assume a window of 24 lines. Then at degree 3, the footprint is 30 lines, which exceeds the window and increases eviction risk. We'll draw a 24-slot cache window and a 30-slot prefetch footprint counter. We can summarize pollution risk with a simple metric. The extra look-ahead beyond 2 is D minus 2 per stream. Across S streams, the excess is S times D minus 2. Divide by the window W to get a fraction. We cap it at 1. So, K equals the minimum of S times D minus 2 over W and 1. With S equal 10, D equal 3, and W equal 24, K is about 0.417. We will use K as the expected fraction of useless prefetches that actually cause extra misses. Now, let us quantify IPC loss when prefetch accuracy is less than 50%. Accuracy is the fraction of issued prefetches that become timely uses. We connect this to performance using a simple miss-based CPI model. Assume base CPI equals 1. Assume baseline demand misses are 10 misses per 1,000 instructions. Assume a miss penalty of 200 cycles. Then baseline CPI is 1 plus 10 times 200 divided by 1,000, which is 3. So baseline IPC is 1 over 3, about 0.33. With prefetching, 2 forces compete. Coverage removes some demand misses. Inaccuracy creates useless prefetches that can evict useful lines, adding pollution misses. We will assume coverage equals 50% and accuracy equals 50% to match the scenario. Saved misses per 1,000 instructions equal coverage times baseline misses. That is 5. Issued prefetches per 1,000 instructions are saved misses divided by accuracy, which is 10. So useless prefetches are 5 per 1,000 instructions. Using our K metric of about 0.417, pollution misses are K times useless prefetches, about 2.08 per 1,000. Therefore, the net MPKI equals 10 minus 5 plus 2.08, which is 7.08. The new CPI is 1 plus 7.08 times 200 divided by 1,000, which is about 2.416, giving IPC of about 0.414. How big is the IPC loss relative to an ideal prefetcher that eliminates all misses? The ideal CPI would be 1. So the ideal IPC would be 1.0. With our less than 50% accuracy scenario, IPC is about 0.414. That is an IPC loss of roughly 59% versus ideal. Key takeaway. With 10 streams, degree greater than 2 makes the prefetched footprint exceed our local window, raising a pollution factor K, which directly reduces the value of inaccurate prefetches. Tuning degree and filtering low-confidence strides is critical. Let's summarize visually. Stride table, 64 entries, 10 active. Degree 3 across 10 streams yields a 30-line footprint. Window 24 implies excess of 6 lines likely to pollute, combined with accuracy under 50%. The useful savings are outweighed by pollution and bandwidth waste, leading to the measured IPC of about 0.414 instead of 1.0. That wraps up our evaluation. We modeled stride table capacity, illustrated why degree greater than 2 increases pollution risk with 10 streams, and quantified performance loss when accuracy is below 50%. The practical advice is to cap degree near 2 to 3 for many stream workloads, and gate prefetches with confidence to keep accuracy high. Thanks for watching.